有讯号吗 ？Okay. Okay. So let's get started. So first, I mean, yeah, it looks like about 2/3, about 60% of students not showing up today. But well, as I said, I mean that's okay. I mean, as long as I mean you guys are able to pick up the material, that's fine with me. But one thing I want to check, okay, because like you guys have the first recitation session yesterday, right? Okay, how many of you went to the recitation session? I mean, can you raise your hand if you have, shown up in the recitation? 1, 2, 3, 4, 5, 6. Okay, 7. So not too many. So totally, how many people showed up? How many students showed up in the recitation? 你们有去的大概几个人？啊，有去的也不知道几个人，大概几个人？I'm not asking you to do like accurate counting. Yeah, 不是精确的计算的，大概几个人？20-30个，10几个，5、6个，6、7个。没有人可以回答啊！你们7个人去的是确定是 recitation 吗？Hello, are you with me now? 你们在这边哦。你们那7个去的有昨天去的，到底大概有多少个人 ？I'm just want to get an estimate. 啊？10几个 ，OK, that's fine, OK. But I just want you guys to know that, okay, we will have like exam, okay, held like using a computer to write the program, and it counts for 20% of this of the total grade, okay. So again, it's okay you don't show up in the recitation, but I highly recommend that you have to practice programming, okay, especially like the algorithms that we covered in this class, okay. 所以你们至少要能够写程式哦。到时候如果说考那个上机的考试的时候，你们都考得很烂，那我们已经尽力帮你了，我们也有安排 recitation 啊。你们不 show up 没有关系，就像我讲的，我们不 take attendance。但是如果你觉得那是我们假设你自己可以学得好，如果你自己学不好，期末不要来找我 ，OK， 好不好 ？OK， 谢谢大家。然后再来 ，OK，Let's continue our discussion about like divide and conquer. Last lecture we actually already covered binary search, right? So I think we talked about this example, and we talked about the time complexity of the binary search, right? Okay. So today we are going to continue discussing the divide and conquer, okay? So the first case, I should have said the second case, because I mean the binary search would be the first case, okay? So the first one that we are going to cover today is powering a number, okay? So powering a number, okay, basically you are trying to compute a to the power of n, where n could be a large integer, large integer. So obviously, the naive algorithm will give you linear time, complexity. What I meant by naive algorithm just means like you write a loop. I think this is like one of the first few questions that you learned from learning the writing a loop, right? I mean, like you just starting from 1, okay, and you keep multiply a, okay, to the result to get a to the power of n. So basically, you just loop n time to get a to the power of n. That's what we call naive algorithm, because the loop structure, okay, runs n times, so it's obviously linear time complexity, okay. But we also could design a divide and conquer algorithm. So what exactly is a divide and conquer algorithm? Basically, okay, we know like a to the power of n would be a to the power of n divided by 2 times a to the power of a to the power of n divided by 2. Okay, this is like according to like the exponential rule. Okay, when n is even, because after all we are dealing with like integers here. So if n is even, obviously we can do things like that. Otherwise, okay, if n is not even, then we get like if n is odd, obviously n minus 1 would be an even number, so it would be a to the power of n minus 1 divided by 2, okay, which will give you an integer times a to the power of n minus 1 divided by 2 times a. Again, this is based on very simple exponential rule. So you could see that every time, okay, the original problem, computation, every time you break the problem by half, but you do need to calculate. You do need to calculate the problem in half size, like this one, okay, twice, and then you multiply them together, assuming the multiplication, okay, takes constant time. Then it is like it's a perfect divide and conquer approach, okay, which will give you, Tn equal to Tn divided by 2 plus theta 1, okay, where n divided by 2, okay, is the cost for you to compute a to the power of n divided by 2. And because you are calculating these two terms, I mean, exactly the same, so you only need to calculate this once, and then you just like doing like a square of the result. So you don't put like a 2 in front. And the multiplication, as I say, it takes constant time, so that's the cost for the merge. And for this one, okay, it's similar. This one is roughly half of the size of the problem. This similar. It's half. These two are the same, so it's like a square of like a to the power of n minus 1 divided by 2. So it's the same thing. Okay, similar. When n is large, n minus 1 divided by 2 or n divided by 2 are basically like similar anyway. Okay, and the multiplication, after you get this term, okay, would be like a constant time. So it's here. So with this, okay, which case of the master theorem applies? In this case, A is 1, B is 2, okay, and we have the power of n for this term to be 0, okay. So because like it'll be case 2, I believe. Like it's like because log BA is 0, and this is I mean this n to the power is also 0. So you just multiply a log n to the 1. So that's like the case 2. Okay, in the master theorem. So actually, this problem, if I remember correctly, because I previously also covered discrete math. Okay, so I covered this problem in discrete math. Okay, previously, I'm not sure if so 你们离散数学谁教的？盛峰老师，他有教这个吗？应该有，是不是 ？OK， 所以 that's good. So okay, so next one, okay, is the Fibonacci numbers. Okay, Fibonacci numbers. We also know Fibonacci number is obviously a recursive definition, okay, in which, f0 is 0, f1 is 1, and for the following terms, fn will be fn minus 1 plus fn minus 2, and this, can be done recursively, okay, when n is greater or equal to 2, okay. There are some variation, different definition of Fibonacci numbers. For example, some people start the f0 from 1, okay, but this perhaps is like the most commonly used definition, okay. Actually, okay, for Fibonacci numbers, the most important part is this recursive formula. Fn equal to Fn minus 1 plus Fn minus 2. So, the initialization, okay, F0 and F1 could be different. Okay, if you want to generalize the Fibonacci numbers. But anyway, okay, come back to this Fibonacci number definition. If you try to expand these Fibonacci numbers, you will get 0, 1, 1, 2, 3, 5, 8, blah, 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 blah. Obviously, like starting from the third term, okay, the number will be the sum of the previous two numbers, okay. So, so how do we calculate the Fibonacci numbers? Okay, if you are getting if I give you an index, okay, I want you to index I want to calculate fi. So what do? Naive recursive algorithm actually is exponential. Okay, so the reason is because in the naive recursive algorithm, when you calculate fi, basically your program, okay, would be something similar to this one. FIB. Okay, barring from like a simple case, for example, like I smaller or equal to 2, well, smaller or equal to 1. Okay. Return, yeah, I is 0, return 0, else if I is 1, return 1, then else just return something like this. Very simple algorithm, okay? But the issue with this algorithm, okay, is that, okay, in the previous example, the example here, you know, we are able to calculate this a to the power of n minus 2 only once. Okay, you can see that we don't have the leading term a here is 1. Okay, we can only do like a t of n minus 2, n divided by 2 once. Okay, because these two terms are the same. Okay, so we just calculate this once and just get the square of it. Okay, but I mean, for Fibonacci numbers, you would argue these two terms are different. So you couldn't just calculate one of them. So if you want to do both of them, what happens is that it's when you calculate FIBN, so you need to call FIB n minus 1, FIB n minus 2, and this one, okay, obviously calls for FIB n minus 2 and FIB n minus 3, and so on. This one will give you, well you have to call, you know, compute FIB n minus 3 and FIB n minus 4, and da da da. So you will discover that this term is the same as this term. This term is the same as this term. You will find that you are doing a lot of repeated works. Okay, a lot of repeated works. So that's why, okay, when you compute the complexity, basically like the complexity of computing a Fibonacci number algorithm, okay, naive one, I'm talking about naive one, okay, it would be like, about the same cost as like Fibonacci number growth, okay, and I hope like in your discrete math class, you have learned that Fibonacci number grows exponentially, okay, and you could even compute like its exponential growth to be like in this basis, this one. So you can compute this one is roughly it's a square root of 2. It's a 2 point something. So it's 3 point something divided by 2. You get like maybe like a 1.6, something like that. Okay, so it's obviously greater than 1. So this one happens to also be called as a golden rule, golden ratio. Okay, I mean, but it doesn't help like to reduce complexity. I mean, this is like exponential, very expensive, because like computing this one, okay, you only get to reduce like 1 and 2, and then you are doing a lot of repeated work. So the complexity, as I said, like if you write it down, it's just like the growth rate of Fibonacci number. Okay, so what do? Actually, it is much easier, okay, if you can calculate, if you can compute f0, f1, f2, blah, 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 up to Fn in the same order. So from the first term to whatever you want to calculate. Okay, because like we know like the next term will be the sum of the previous two terms. So you just need an array. You just need an array. Okay, you just put the numbers into the array. Okay, we write a very simple loop. Okay, starting with like the index 0, index 1 to be 0 and 1, and your loop start from like 2, and then every time you just calculate like the index position, okay, to be the sum of the previous two positions. That's it. So this algorithm obviously runs in linear time. Again, this is a very simple loop structure. So the running time is linear to the size of n. So obviously, linear time is much, much better than exponential time, right? So that's like, again, this example shows you like, the importance of like considering complexity of your algorithm. Because to be really honest, this algorithm obviously is easier. I mean, you can write it like in like just 1 minute from the definition of the recursive Fibonacci numbers, and then obviously it also is correct. But the issue is, the complexity is very bad. Okay, it's very bad. So this is also one example that show you, okay, although 99% of time, or I probably should say 90% of time, okay, divide and conquer concept or like a recursive like approach usually helps, but in some particular situations you need to be very especially careful, okay, when you make recursive calls. Okay, so there's also a naive recursive squaring. What is this? Because we are again, this is like what you learn from discrete math. Okay, in the discrete math, actually you are told to solve this directly, because you have in a discrete math, like you can solve like the recursive formula directly, right? And if you apply the concept like to solve the recursive formula of the Fibonacci numbers, it's going to give you something like this. So Fn is somewhere like a theta to the power of n divided by square root of 5, rounded to the nearest number, okay, nearest integer. So this is like a, analytical, like approximation solution for Fibonacci number. Okay. So with that, because this is obviously you just need to calculate this like a number to a certain power, right? So in this case you can apply recursive squaring, which is this one. Just apply this algorithm to get like theta to the power of n, okay, and then take constant time to divide that result by square root of 5. So obviously, I mean, it gives you log n time complexity. Okay. However, okay, this method is unreliable because like a lot of time, I mean, when you are asked to calculate Fibonacci numbers, what we want is like the accurate numbers, okay, not just like approximation. Okay, this is more like approximation. Okay, so why is it approximation? Because like a floating point arithmetic is prone to round-off errors. So there are like a round of errors, I mean, in here. So it's impossible to get like a very accurate result anyway. Okay, so here for Fibonacci numbers, I'm giving you 3 different solutions. Okay, depending on the situations, okay, you may apply, okay, different solution. I mean, the naive recursive squaring could be used in case if you are not asked to, I mean, for like a very accurate estimate. Maybe you only ask to like to get like the estimate of a Fibonacci number fib n, where n is a very large number. Then, calculating this one by the recursive squaring is a good idea. So let's have a closer look at the recursive squaring. Okay, so we know like Fibonacci numbers. Okay, its recursive form can be written, in one very simple matrix form. Okay, like this. Okay, and I call this a theorem. Obviously, I need to prove it, right? Okay. But I mean, the reason we can use recursive squaring is that calculating Fn is like calculating a matrix with to a power of n. So I mean, obviously, I mean this thing. Where is it? This thing can be applied, can be generalized to matrix multiplications. Okay, so if we can take the fact that the Fibonacci number, according to the definition, is this one, then we can use the recursive squaring algorithm directly. Okay, I mean, but what do we do? Does the recursive, I mean, this will be a very accurate one, okay, because we are using matrix to compute it, okay. So we first need to prove this theorem, okay. For the base case, this is very simple. When n is 1, okay, I mean, obviously, F2, F1, F0, I mean, they are 1, 1, 0. So this is obviously true, okay. So in the case, okay, of because we are using induction, so we need to assume like it works when I mean for smaller number, and now we are trying to see like for example like Fn plus 1, okay. So we use this one, okay, equal to, which will be the same as this one times this one, okay, and according to this theorem, okay, and then for this one we can apply our the induction hypothesis. So this one will be, okay, this one. Okay, so this one times this one, it will be this one. So it's a very straightforward computation, and you can get the result. So we prove this theorem, okay, by using the recursion, okay, and with that, as I said, okay, we can formulate the Fibonacci numbers into, something to a power. In this case, is a matrix, and then we can apply the this algorithm, okay, which is very nice because it's a log n time complexity. So far so good, right? So far so good, right? So since we are in position to talk about matrix, okay, let's try to think about how we can optimize the matrix multiplication. Okay, in here, okay, we are considering multiplying two square matrices. Okay, so I mean the A, okay, is denoted like this. B is denoted like this. And the C would be the result of A times B. So, I mean, we have, if you, write it like write it out in the matrix format, it's going to be, we know like a Cij, okay, any particular term in the matrix C will be, like this. Right? So this is like a matrix multiplication that you have learned, like 你们什么时候第一次学 matrix 啊？高中吗？大学 ？Okay, but this is pretty straightforward, right? Okay. Because we are talking about like a square matrices, okay, square matrices. Okay, so a very naive algorithm. Okay, again, okay, this is like perhaps one of the few examples you learned from loops, structure, is that okay? You can do this thing, okay? You can calculate like a Cij by applying, because Cij obviously, I mean, you need to, go through all different I and j, okay, and for each given I and j, okay, I mean, you need to have a loop for k to compute the Cij, and you have different I and different j, so so obviously it calls for like a 3 nested loop. Okay, 3 nested loops. So because this is a very simple, but it's a nested loop structure, okay, we have 3 levels, okay, basically I, j, and k, okay. So each index runs for like linear to like the size of n. So this obviously gives us the running time n cube, right? So, can we do better? And I told you guys that, okay, if we are able to like use like a divide and conquer approach, most of the time we are able to reduce the time complexity. Okay, so the idea is like this. Okay, we try to let's try to make the case easier for discussion. Okay, let's assume that n, okay, n times n, that number n in the n times n square matrix, okay, that number n is an even number. Okay, for odd number, we will deal with like a corner cases later. Okay, later. So if n is even, we can break like this n times n matrix into 4 matrices, okay, of n divided by 2 times n divided by 2 sub matrices. like this. Okay, where capital A matrix will be like this, capital B matrix will be like this, and this represent the capital C matrix. Okay, so if we represent in this representation, obviously, the lowercase a, b, c, d, e, f, g, h, and r, s, t, u, each one of them represent an n divided by 2 times n divided by 2 matrix, okay? And this type of submatrix, I mean, I assume like you already took like a linear algorithm, okay? In the linear algorithm, you should have learned, okay? 因为我刚好也在教线性代数啊 okay? So maybe some of you are in my class, okay? Some of you are maybe in Professor Su's class, okay? So anyway, you should have learned that, okay, if you represent the matrix in the submatrices format, okay, basically you can also do like a matrix multiplication, something like this, where you are getting, you know, R equal to AE plus BG, S equal to AF plus BH, and so on. So you have all these formulas. But keep in mind that each of these variable represent a submatrix, okay? So this is very simple, I mean, you know, divide and conquer, right? Divide and conquer. So, so previously we are computing the, what should I say, like, you know, multiplying two n times n matrices. Now we are trying to, you know, compute for each of them, because this one, each of these calls for like a one matrix multiplication, but the problem size is reduced to n divided by 2 times n divided by 2 matrices, right? So we have like A multiplies of, you know, this like submatrices, okay? And also we have 4 additions. Basically, like after we finish the computing, this multiplication, we need to add them up to form our R, S, T, and the U. Okay? So, well, so if we represent this thing, this is obviously recursive, I mean, approach, okay? And then we, you know, we try to, I mean, consider this thing, you know, into like a, you know, recursive formula. We consider it's like a time complexity. We know like a T of n, where n represent like multiplication of two n by n matrices, okay? So T of n, okay, now is broken into like a multiples of like A multiples of like submatrices. Each of them is like you know, of size n divided by 2. So we have this. But how about like the merge? How much effort? What is the complexity for this merge? Okay, so well, each of these results n divided by 2 by n divided by 2, right? So we need to, you know, sum them up. Now, basically, you know, like how to sum two matrices, right? So it is linear to the number of elements, right? So how many elements do we have for the result for this thing? So each one is like n divided by 2 times n divided by 2, this many elements, right? So the order will be n squared, right? The order will be n squared. Okay? And then, you know, you need to do this 4 times. You have 4 matrix additions. Okay, but since the number of additions is a constant, so it doesn't change the complexity. Okay, so the merge, okay, in total, the complexity is big O n squared. Okay. Of course, there are some leading constants. Okay, but we can omit those constants when we consider the time complexity. So that's why we are getting this thing. Okay? So, is it good? In this case, A is 8, B is 2, and the n to the power of 2, right? So if you try to see like the complexity of this recursive formula using the master theorem, because log 2, 8 will give you 3. So n to the power of 3 is in higher order than, well, with a constant order higher than the n to the power of 2. So obviously the time complexity here is still n cubed. It's case 1. So we go through all these troubles, okay, to do like a divide and conquer algorithm. And previously I told you divide and conquer usually can give you a better complexity, but this is obviously not the case, right? Because the complexity remains the same. It's n cubed, right? So what do we do? In fact, okay, there's some optimization we could do in here. The purpose, okay, the purpose would be to get R, S, T, and U in this format, right? Yeah, that's our goal. That's our goal. But how can we, use fewer number of multiplication and then still be able to get these terms? That's the tricky part. That's the tricky part. And that's the contribution of this guy called Strassen. Okay. This Strassen, okay, he is able to get the result, okay, of all those like submatrices by only 7 like multiplications of those submatrices. Okay, only 7 multiplication. How does he do it? Okay, basically, okay, forget about RSTU. RSTU looks like this. We know that. Yeah, we know that. But let's forget about RSTU first. This guy is like a kind of like a, very clever, okay? He doesn't compute RSTU directly. He compute P1, P2, P3, P4, P5, P6, and P7. Okay? From those like submatrices. So each of them, you can see that, okay, yeah, it takes some, maybe subtraction, addition, things like that. But you can see each PI require only 1 multiplication. Is that right? Each PI require only 1 multiplication. Okay? And then, okay, he can use these PIs to reconstruct the RSTU. R is P5 plus P4 minus P2. S is P1 plus P2. T is P3 plus P4. U is P5 plus P1 minus P3 minus P7. Of course, you know, this computation involves no additional multiplication of submatrices. Okay? So yeah, I mean, you can see that we need to do a lot of submatrix addition or subtraction. Yes, we need to do that, those addition subtractions. But we do in the process, we do save like one submatrix multiplication. Is that right? Some of you may not, you know, for example, let's just take a look at R. Okay, R is I mean, R is P5